Then once the bridge breaks here, it's once again going to find a new equilibrium, this time with only the two supports on one side of the bridge. This is going to result in a bending diagram that looks like this, where the main span is cantilevering from the edge two supports, where we'll see a lot of compression here and then a lot of tension in this side. Now if we consider that this is designed as an arch where the center of the span is very thin, it's possible that it's not suited for any real increase in bending like we see in the second frame. Then slightly to the right, there's a point of zero moment in the top situation, which corresponds to a really large increase in moment in the new situation. So it kind of makes sense why we see failure at the thinnest part of the truss, and then a little bit to the right before the support. This leaves us with our last stable position, where the truss is simply supported by the two end supports, where both supports are now in compression. With the support on the right now experiencing compression, there's an additional force added when it breaks. You'll see that the bridge starts to rotate around that main pier. And what this does is it applies an additional force on that right pier, which is now experiencing compression and this additional force, which makes sense why that there's an additional failure here and the bridge continues to rotate, toppling this pier. Or theoretically, there's a larger shear force in this end of the bridge, and that's what causes the failure. So yeah, that concludes this exercise in analyzing the collapse. And I'd like to reiterate that this is not a professional forensic analysis of the bridge. I yield any conclusions that I may have claimed here to the official NIST investigation of the collapse.